Okay, so hello to everyone. I'm going to talk about minimal session types. This is a joint work with my advisor Jorge Pérez and fellow student Erik Voogd. So message passing concurrency is very relevant today as more and more software system crucially depends on the communication. And it's also supported by various programming languages nowadays, such as Go or Cloud Haskell. And we will consider a typical e-commerce protocol in which we have 3 participants. So first, buyer wants to interact with the seller. It sends a book title. Then seller responds with the price of the book. And after that, the bank details. And then the buyer asks a payment service to carry on the payment on his behalf. So it sends the price and the bank details and then waits for the status message if this payment is actually carried on. And if this is all good, then it sends address. And verifying correctness of implementation of each of these participants is very tricky. And many bugs can be introduced. So for example, if seller swaps the order of the actions, or if the message with wrong type, not wrong, but the type that is not expected on the other end is dispatched. And bugs that also can lead to deadlock system. So in our work, we focused on type-based approach to communication correctness, which are session types that have been widely developed, have many variants and implementations. And the main idea behind the session type is that we attach a type to each communication channel, and the session type tells what and when should be exchanged through this communication channel. And the correctness follows from type level compatibility, that is duality of endpoints of communication channels and linearity of the actions of a session. So if we want to type a payment service endpoint if this communication with the buyer, we can attach this type to communication channel. So this is a payment service viewpoint of a channel. So it first says that it expects to receive the message of type integer, then string, then as the answer it sends a boolean, and then finally this channel terminates, so it's not capable of doing any more actions. And we can see that key feature is sequentiality that actually enable us to structure this communication protocol that we want to have. And this sequencing is achieved by this semicolon. But if we look at one possible implementation in pi calculus, we can also see that sequencing is also present on the process level, where it's denoted by dot. And we can see that sequencing goes hand in hand on type level and in process level. So that not very good side of a session types is actually their implementation in practice. Since some key features of session types are not supported by type system for actual programming languages. So for example, channel creation in Go. Well, when we want to create a channel in Go, we only specify the type of a payload value. And additionally, when we want to use this channel, we can specify its direction. And in Cloud Haskell, when we create channel, we actually create its 2 endpoints with also only specifying payload value of this channel. So if programmer wants to have some sort of protocol structure, he has to do that manually, and this is of course tedious and error prone. And if we consider a few recent developments of implementation, we actually noticed that the common to all of these approaches is a sort of detour from session type theory. So for example, recent work of Scala's at ECOOP 2016, they provide a lightweight implementation of session type in Scala, where programmer actually has to refactor code in order to provide continuation channels, and linearity is checked dynamically. So what we want to do is to bridge this gap between session types theory and practice without the help of detours. So the question we asked is, can we dispense with sequentiality in session types? And in this talk I will show that the answer to this question is yes. So we provide a translation such that sequentiality in session types is actually codified in sequentiality on process level. And by doing that, we show that having sequentiality on both session types and process level is redundant. So our main contribution, what we call minimal session types. So minimality comes from absence of sequentiality. And these types are much closer to the types already available in actual programming languages. So for example of minimal session types, we have a channel endpoint that uses that only expects to receive a value of type string and then terminates, or the other that expects to receive a tuple of integer and boolean and then terminates. So our work can be seen from 3 different perspectives. So formally, we provide a typed compilation of session type processes into processes that uses only minimal session types. From a more conceptual standpoint, this work presents, to the best of our knowledge, the first study of absolute expressiveness of session types. That is, we explain session types in terms of themselves. And more pragmatically, this can present a new way of integration of session types into actual programming languages. So this slide sums up all the main ideas of how we do that. So if we have a process P that uses the channels with standard session types, we codify the sequencing of the session types of these channels into the decomposition of P. And along that, each session type, we break down it into the list of minimal session types. So for example, if we have a process P from the running example that uses the channel U that has a standard session type, we will translate that to its decomposition, which essentially consists of 3 processes in parallel. So this number is correspondent to the number of actions of original session type. And each of these processes actually mimic one action of the original channel. And each of the channels that this uses has a minimal session type. So in order to recover sequentiality that we lost, all of these processes also have an extra mechanism to ensure the order of execution. So by doing that, we show that sequencing in session types is indeed redundant. And our main typability results said that if process P is typable under the standard session types, then its decomposition is typable under the list of minimal session types. So for our work, we consider particular calculus, so that is HO, for the reason being that it's a very compact calculus that models mobile code. So HO stands for higher order. And it's compact in the sense that it only supports passing of abstractions, and only abstractions of this form, that is functions from channels to processes. So it does not support name passing, it does not support recursive processes, but it has recursive session types, and it has all other usual PyCalculus constructs as name restriction, label choice, and so on. Its type system is usual session types system, extended with linear and shared functional types. And the type soundness of this type system ensures fidelity and safety of the communication. And as I said, it does not support name passing and recursive processes, but can fully abstractly encode both of them. So it's very expressive. So to get back to our running example, for the simplicity, we will focus on this portion of the example. where the buyer sends the price to the payment service, and then after that bank details, and then expects to receive an answer. So we will provide a simple implementation of the payment service first. So in a job, so it first expects to receive an integer, then bank details as a string, and then it just checks if this price is within the limit and sends the boolean as an answer back. So we want to decompose that. We will first decompose the channel U such that each of these new channels has a minimal session type. But by doing that, we lose any dependencies between channels. And in order to recover that, we will actually generate 3 processes in parallel. And we will have these additional structures of new channels C that we call propagators. And the purpose of these propagators is first to codify this sequentiality that we lost, and also to propagate variable bindings. So for example here, when we bound A, it's going to be propagated until the point of its use. And if A has a linear functional type, then we wouldn't propagate that along. Actually, this structure is inspired by Pérez's work on trios. Very similarly, we can decompose the client process or the buyer. Also, only keeping in mind that we have to have a fresh propagator's name. And if we want to put these 2 processes in parallel, we will decompose this parallel composition as what we call, or what Pérez calls, a control trio. So that's a trio that triggers these 2 decomposition in parallel. And it's also compositional, so if this is a part of some bigger process, it can wait for this outer process to activate it. So this is a story about processes, and now we will see what happens with types. So if we start with this implementation of the payment service, it uses the channel with the standard session type. Its decomposition consists of these 3 processes in parallel, essentially. And each of these channels U that mimics the regional action has a minimal type. But also, all propagators named that we introduce, they also have a minimal session types, as we can see here. And this is the purpose of this, to intuitively justify our typability result. So what we have to do is to break down the types of U and also to provide the types of C, which we can do on every binding occurrence. We can find out the types of the propagators channels. So to sum up, what we did is we provide explanation of session types in terms of themselves. That is, we studied their absolute expressiveness. So from theoretical standpoint, since we detect this redundancy in session type theory, this can potentially streamline other session type frameworks. And from the more practical standpoint, our work bridged the gap between session type theory and the type system that are already present in actual programming languages. So in this talk, I focused on a very simple example and like a very small subset of age O. And in paper, there is much more. So we have 2 extensions, that is decomposition of label choice and also recursive processes, that is recursive session types. So by doing that, we actually cover whole entire AJO calculus. And also for decomposing these 2, we actually leverage like full power of abstraction passing. Also, we provided 2 convenient optimizations of our decomposition. That is that we can dispense with polyadic communication in this breakdown. And and the other is that we can translate from trios, that is processes with maximum 3 sequential prefixes, into duos, that is processes with maximum 2 sequential prefixes. So for the ongoing work, from theoretical standpoint, we are working on the proof of operational correspondence between process P and its decomposition via typed bisimilarities or behavioral equivalence. And from more practical standpoint, we are working on extending our artifact, Misty, such that it generates a Cloud Haskell code out of sort of Cloud Haskell with session types. And this actually concludes my talk. Thank you.
Thank you. So we have time for questions. Okay.
Thanks. So you use this word redundant. I'm trying to figure out what that means in this context. So normally if somebody told me, oh, the sequences are redundant, I'd say, oh, by encoding you can get all the same information into the types. But you don't have the same information. You've thrown away the sequentiality in the types. You're depending on the program that you're translating to recover that information. Right? And the first thing you said that's nice about session types is if you conform to the session type, then you know that you don't get the messages out of order.
Yeah.
But after you've done this compilation, that is no longer true.
Yeah, so, yeah, but if we have this sort of translation, then we can actually preserve all the benefits of sequentiality, but translate that to something that is closer to types of the programming language which doesn't have any sort of sequentiality.
Okay, so you said we preserve all the benefits of sequentiality. One of the benefits of sequentiality is exactly what you said, that if you conform to the session type, you know that your server won't get the messages out of order. How do you preserve that benefit?
So we don't want to get rid of like session types as they are now. We just provide like a minimal form of that. So if we can translate, so for example, in this example of what we want to do like with Cloud Haskell is like to extend Cloud Haskell such that programmer can write actually session type, but then we can translate that to something that is acceptable by Cloud Haskell now. So like as a compilation step.
Right, so calling it compilation, I understand. It's your use of the words redundant or talking about a minimal language rather than just a different lower level language that preserves fewer invariants. I understand that. But you seem to be saying we lose nothing, or even the minimal term suggests, oh right, you only need this to carry all the information. But no, when you go into the minimal one, you've thrown away really useful information that you're preserving by other means.
Okay, I see what you mean.
And then I also want to ask, there's another transformation, I think due to Ornella Darda and San Giorgi, where they do sort of a continuation passing style.
Yes, yes.
And that would also have the property that the particular channels don't change, but by passing back another channel, they do encode the sequentiality into the types. So I just want to ask how those two techniques relate.
Yeah, so I think they were like quite much, but the difference is that they target like linear types for pi calculus, and we stay within the session types theory.
Well, for instance, if I want to compile to Cloud Haskell, I think I might be tempted to use their technique rather than your technique. So I was going to say, as you're going to go on and do this work, looking at compiling into Cloud Haskell, I think it'd be really nice if you also implemented their technique, and then you can compare the two.
Like, you mean just in order to compare it, or?
Yeah, which is a better way of doing the compilation?
Yeah,
what are the trade-offs?
Yeah, it's interesting. For example, also like how many extra channels it uses, or things like that. Like this overhead to compare also.
Yeah, my guess is that you're both sort of using one channel per message exchanged. So that'll probably the comparison there will be about the same. But I think there might be other interesting differences.
Okay, thanks. So let's thanks Alen again. Okay, so next talk will be